There are various kinds of nanomaterials. And therefore, there exists various types of methods and routes of making nanomaterials. Some of the methods can be expanded in scale for the industry level, while some methods are still remained at lab scale. As you have seen, there exists a variety of inorganic or organic nanomaterials such as nanoparticles such as gold nanoparticles in the leftmost corner of this figure, nanocrystals, nanowires, nanosheets, nanorods, graphene, nanotubes, and so on. Some of the nanomaterials exhibit very regular size and shape as well crystallinity. However, some of them exhibit relatively irregular size and shape such as titanium nanoflower or tin oxide nanoflower. Some of the nanomaterials can be synthesized in continuous manner, while some of them are only prepared in batch reactor. Some of them are easy to synthesize, while some of them requires year-long synthetic way. We are dealing with very fine structures. A nanometer is a billionth of a meter. This indeed allows us to think in both the bottom-up or the top-down approaches to synthesize nanomaterials, that is either to assemble atoms together or to disassemble, break, or dissociate bulk solids into finer pieces until they are constituted of only a few atoms. This domain is a pure example of interdisciplinary work encompassing physics, chemistry, and engineering up to medicine. For example, let's think about the preparation of nanoparticles. When you start with bottom-up approach, this means that you need to start with basic building blocks whose size is much smaller than nanoparticles. It means that you need to think about assembly of molecules or atoms using specific methods such as Sogel process, pyrolysis, chemical reaction in liquid phase, chemical vapor deposition in gaseous phase, and so on. To use the bottom-up approach, therefore, it is important to know about the molecular interaction at fundamental level and basic principles of physics and chemistry as well as molecule biology. In contrast, when you start with top-down approach, you can start with materials whose size much bigger than nanoparticles. It is like sculpting a rock into a figure. For example, you can use mechanical process such as ball milling, chemical process such as chemical etching, laser ablation, sputtering, electroexplosion, and so on. Then which way should you think of for the preparation of nanomaterials? It depends on your goal, time, and cost. For example, if you want to prepare nanoparticles with regular size and shape, you are recommended to use bottom-up way such as chemical reaction followed by precipitation. This way is also advantageous in expanding the production scale for the industrial applications. If you want to prepare semiconductor nanowires onto some specific substrate, you are recommended to use gaseous phase top-down approach such as chemical vapor deposition. However, it is limited to be expanded to industrial level. There are many different ways of creating nanostructures, of course. Macromolecules or nanoparticles or buckyballs or nanotubes and so on can be synthesized artificially for certain specific materials. They can also be arranged by methods based on equilibrium or near-equilibrium thermodynamics such as methods of self-organization and self-assembly, sometimes also called biomimetic processes. Using these methods, synthesized materials can be arranged into useful shapes so that finally the material can be applied to a certain application. First of all, let us think of top-down methods such as mechanical attrition, where the material is prepared not by cluster assembly but by the structural decomposition of coarser grained structures as the result of severe plastic deformation. This has become a popular method to make nanocrystalline materials because of its simplicity, the relatively inexpensive equipment needed, and the applicability to essentially the synthesis of all classes of materials. The major advantage often quoted is the possibility for easily scaling up to tonnage quantities of material for various applications. Similarly, the serious problems that are usually cited are 1. Contamination from milling media and/or atmosphere, and 2. To consolidate the powder product without coarsening the nanocrystalline microstructure. In fact, the contamination problem is often given as a reason to dismiss the method, at least for some materials. Here we will review the mechanisms presently believed responsible for formation of nanocrystalline structures by mechanical attrition of single-phase powders, mechanical alloying of dissimilar powders, and mechanical crystallization of amorphous materials. The two important problems of contamination and powder consolidation will be briefly considered. Mechanical milling is typically achieved using high-energy shaker, planetary ball, or tumbler mills. The energy transferred to the powder from refractory or steel balls depends on the rotational, vibrational, speed, size and number of the balls, ratio of the ball to powder mass, the time of milling and the milling atmosphere. Nanoparticles are produced by the shear action during grinding. Milling in cryogenic liquids can greatly increase the brittleness of the powders, influencing the fracture process. As with any process that produces fine particles, an adequate step to prevent oxidation is necessary. Hence this process is very restrictive for the production of non-oxide materials, since then it requires that the milling take place in an inert atmosphere and that the powder particles be handled in an appropriate vacuum system or glove box. This method of synthesis is suitable for producing amorphous or nanocrystalline alloy particles, elemental or compound powders. If the mechanical milling imparts sufficient energy to the constituent powders, a homogeneous alloy can be formed. Based on the energy of the milling process and thermodynamic properties of the constituents, the alloy can be rendered amorphous by this processing. The wet chemical synthesis is the most well-known bottom-up approach for the production of nanomaterials. The first way of wet chemical synthesis is the sol-gel process. This process involves the evolution of inorganic networks through the formation of a colloidal suspension, which is called sol, and gelation of the sol to form a network in a continuous liquid phase, which is called gel. The precursors for synthesizing these colloids consist usually of a metal or metalloid element surrounded by various reactive ligands. The starting material is processed to form a dispersible oxide and forms a sol in contact with water or dilute acid. Removal of the liquid from the sol yields the gel, and the sol-gel transition controls the particle size and shape. Sol-gel processing refers to the hydrolysis and condensation of alkoxide-based precursors such as tetrathyl orthosilicate. The reactions involved in the sol-gel chemistry based on the hydrolysis and condensation of metal alkoxides. Sol-gel method of synthesizing nanomaterials is very popular amongst chemists and is widely employed to prepare oxide materials. The sol-gel process can be characterized by a series of distinct steps such as 1. Formation of different stable solutions of the alkoxide or solvated metal precursor. 2. Gelation resulting from the formation of an oxide or alcohol bridge gel network by a polycondensation reaction that results in a dramatic increase in the viscosity of the solution. 3. Aging of the gel, during which the polycondensation reactions continue until the gel transforms into a solid mass, accompanied by contraction of the gel network and expulsion of solvent from gel pores. Ostwald ripening, which is also referred to as coarsening, and phase transformations may occur. The aging process of gels can exceed 7 days and is critical to the prevention of cracks in gels that have been cast. 4. Drying of the gel, when water and other volatile liquids are removed from the gel network. This process is complicated due to fundamental changes in the structure of the gel. The drying process has itself been broken into 4 distinct steps. First, the constant rate period, second the critical point, third the falling rate period, fourth the second falling rate period. If isolated by thermal evaporation, the resulting monolith is termed as irregular. If the solvent such as water is extracted under supercritical or near supercritical conditions, the product is an aerogel. 5. Dehydration, during which surface-bound ammo groups are removed, thereby stabilizing the gel against rehydration. This is normally achieved by calcining the monolith at temperatures up to 800 degrees Celsius. 6. Densification and decomposition of the gels at high temperatures, T800 degrees Celsius. The pores of the gel network are collapsed, and remaining organic species are volatilized. The interest in this synthesis method arises due to the possibility of synthesizing non-metallic inorganic materials like glasses, glass ceramics or ceramic materials at very low temperatures compared to the high-temperature process required by melting glass or firing ceramics. The major difficulties to overcome in developing a successful bottom-up approach is controlling the growth of the particles and then stopping the newly formed particles from agglomerating. Other technical issues are ensuring the reactions are complete so that no unwanted reactant is left on the product and completely removing any growth aids that may have been used in the process. Also, production rates of nanopowders are very low by this process. The main advantage is one can get mono-sized nanoparticles by any bottom-up approach. The gas phase synthesis methods are of increasing interest because they allow an elegant way to control process parameters in order to be able to produce size, shape and chemical composition. Controlled nanostructures. Before we discuss a few selected pathways for gas phase formation of nanomaterials, some general aspects of gas phase synthesis needs to be discussed. In conventional chemical vapor deposition, abbreviated as CVD synthesis, gaseous products either are allowed to react homogeneously or heterogeneously depending on a particular application. 1. In homogeneous CVD, particles form in the gas phase and diffuse towards a cold surface due to thermophoretic forces, and can either be scrapped off from the cold surface to give nanopowders, or deposited onto a substrate to yield what is called particulate films. 2. In heterogeneous CVD, the solid is formed on the substrate surface, which catalyzes the reaction and a dense film is formed. In order to form nanomaterials, several modified CVD methods have been developed. Gas phase processes have inherent advantages, such as an excellent control of size, shape, crystallinity and chemical composition. Relatively easy synthesis of highly pure materials with multi-component systems. This is mainly due to a fact that the condensation occurs only when the vapor is supersaturated, and in these processes homogeneous nucleation in the gas phase is utilized to form particles. This can be achieved both by physical and chemical methods. The simplest fashion to produce nanoparticles is by heating the desired material in a furnace in a heat-resistant crucible containing the desired material. This method is appropriate only for materials that have a high vapor pressure at the heated temperatures that can be as high as 2000 degrees Celsius. Energy is normally introduced into the precursor by arc heating, electron beam heating or Joule heating. The atoms are evaporated into an atmosphere,
which are either inert gases or reactive precursors. To carry out reactive synthesis, materials with very low vapor pressure have to be fed into the furnace in the form of a suitable precursor such as organometallics, which decompose in the furnace to produce a condensable material. The hot atoms of the evaporated matter lose energy by collision with the atoms of the cold gas and undergo condensation into small clusters via homogeneous nucleation. In case a compound is being synthesized, these precursors react in the gas phase and form a compound with the material that is separately injected in the reaction chamber. The clusters would continue to grow if they remain in the supersaturated region. To control their size, they need to be rapidly removed from the supersaturated environment by a carrier gas. The cluster size and its distribution are controlled by only three parameters such as the rate of evaporation, the rate of condensation, and the rate of gas flow. Because of its inherent simplicity, it is possible to scale up this process from laboratory to industrial scales. The second way for the gaseous synthesis is flame-assisted ultrasonic spray pyrolysis. In this process, precursors are nebulized and then unwanted components are burnt in a flame to get the required material. For example, zirconia has been obtained by this method. Flame hydrolysis, that is a variant of this process, is used for the manufacture of fused silica. In the process, silicon tetrachloride is heated in an oxyhydrogen flame to give highly dispersed silica. The resulting white amorphous powder consists of spherical particles with sizes in the range 740 nanometers. The combustion flame synthesis, in which the burning of a gas mixture, for example acetylene and oxygen or hydrogen and oxygen, supplies the energy to initiate the pyrolysis of precursor compounds, is widely used for the industrial production of powders in large quantities, such as carbon black, fumed silica and titanium dioxide. However, since the gas pressure during the reaction is high, highly agglomerated powders are produced, which is disadvantageous for subsequent processing. The basic idea of low-pressure combustion flame synthesis is to extend the pressure range to the pressures used in gas phase synthesis and thus to reduce or avoid the agglomeration. Low-pressure flames have been extensively used by aerosol scientists to study particle formation in the flame. A key for the formation of nanoparticles with narrow size distributions is the exact control of the flame in order to obtain a flat flame front. Under these conditions, the thermal history, that is time and temperature, of each particle formed is identical and narrow distributions result. However, due to the oxidative atmosphere in the flame, this synthesis process is limited to the formation of oxides in the reactor zone. The third way for the gaseous synthesis of laser ablation. This method has been extensively used for the preparation of nanoparticles and particulate films. In this process, a laser beam is used as the primary excitation source of ablation for generating clusters directly from a solid sample in a wide variety of applications. The small dimensions of the particles and the possibility to form thick films make this method quite an efficient tool for the production of ceramic particles and coatings, and also an ablation source for analytical applications such as the coupling to induced coupled plasma emission spectrometry. The formation of the nanoparticles has been explained following a liquefaction process which generates an aerosol, followed by the cooling, solidification of the droplets, which results in the formation of fog. The general dynamics of both the aerosol and the fog favors the aggregation process, and micrometer-sized fractal-like particles are formed. The laser spark atomizer can be used to produce highly mesoporous thick films, and the porosity can be modified by the carrier gas flow rate. Zirconia and tin oxide nanoparticulate thick films were also synthesized successfully using this process with quite identical microstructure.
Synthesis of other materials such as lithium manganate, silicon and carbon has also been carried out by this technique. One of the advantages of the gaseous phase synthesis of nanomaterials is that it is possible to prepare various shaped nanomaterials such as nanowires, nanotubes, nanorods, nanosheets, nanoribbons, and so on. For the nanowires and nanorods, gaseous phase transport methods such as chemical vapor deposition or laser ablation can be used. The synthesis of nanorods or nanowires is due mainly to the phase transition of gaseous phase precursor molecules. For example, the growth of silicon nanowires is initiated with vapor transport of silicon precursors in the catalytic metal nanoparticles such as gold spheres as shown in the left figures. The transported precursors diffuse in the gold nanoparticles, forming temporary alloy. However, the alloy is thermodynamically unstable since silicon molecules in the gold are supersaturated. The thermodynamics instability can be relaxed by the extraction of the supersaturated silicon molecules in liquid phase, and the extracted liquid phase suffers phase transition from liquid to solid since the surface temperature of the gold is lower than the melting point of silicon. The continuous supply of the vapor phase silicon precursors molecules into the gold nanoparticles leads to the directional growth of extracted solidified silicon, which turns into the long nanowires or nanorods. The growth rate, direction, and shape or even crystallinity of the nanowires can be controlled by the size and shape of the gold nanoparticles. This growth is called as vapor-liquid-solid or VLS mechanism. Another mechanism for the growth of nanowires and nanorods is vapor-solid mechanism without the aid of liquid phase intervention. In this mechanism, there is not metallic catalytic nanoparticles such as gold nanoparticles as was used in the VLS mechanism. Instead, there are metal and precursor alloy nanoparticles, which works as both catalyst and reactants. For example, the growth of zinc oxide nanowires can be initiated by the zinc-tin alloy nanoparticles. When oxygen gases are introduced into this alloy nanoparticles, oxygen molecules react with zinc, and form the crystalline zinc oxide solid, which emerges right beneath the nanoparticles. When the given amount of the zinc in the nanoparticles are completely consumed for the growth of the zinc oxide nanowires, the growth is terminated. This growth mechanism is similar to the VLS mechanism. However, there is no liquid phase of the extracted supersaturated materials. It is also possible to prepare nanomaterials via various synthetic ways. For example, in the case of nanosheets or nanoplatelets, we can use mechanical exfoliation. Actually, this method is popular for the preparation of graphene too. By using chemical intercalation, it is also possible to obtain 2D nanomaterials such as MXene. By using CVD, nanosheets can be grown on the catalytic substrate such as gold-coated silicon wafer. Finally, using molecular self-assembly, various shapes of nanomaterials can be prepared. In recent years, there are vast amount of interest in the properties of 2D nanomaterials such as two-dimensional transition metal dichalcogenide, graphene, silicone, hexagonal burinitride, and so on. One of the promising ways to prepare the two-dimensional nanomaterials is to employ the graphene as the molecular substrate as shown in the right figure. Using the atomistically periodic and perfect substrate, we can grow inorganic nanostructures, organic molecules clusters, periodic nanostructures, and so on.